Half an hour.
Yeah, I don't have
So he's not moving the camera. This automatic sensor. So
Yeah,
it should
but
move.
picking.
No, it's not because he's standing in one place and it's moving away.
That's what I'm saying. So it's picking something else. No?
Maybe it's,
If I move, probably not.
But it's current. Why is it currently moving? Is the question.
Thank you, sir.
Maybe once you move to the chalkboard, it will focus.
Yeah. I have the same positive.
You're not worried.
So welcome to the last talk of today's today's second day. So now Professor Kastin here will talk about random polytopes.
Yes, thank you very much, and I would like to thank the organizers for inviting me here. And first time I came to India. It's very pleasant and exciting and fascinating experience. You know, in most countries, men take great pride in how they drive their cars. Now, if I had any of that, it evaporated as soon as I came to Bangalore. So, my plan certainly was to talk about random polytopes. I hope I will do this at the end. But mainly, I want to talk about the affine surface area. Because this notion shows up in all kind of formulas and problems in random polytopes or the approximation problems. And so, as usual, a convex body is a compact convex subset over N non-empty interior. Yeah, so I talk about the affluent surface area, and then my talk will be a little bit intertwined with that of Elizabeth. And so sometimes I might repeat this or that, but I hope I won't do that too often. So the affine surface area, or we call it here A S of K, where K is a convex body, is the integral over the boundary of K. And then we have here kappa on the boundary of K. This is the curvature here. Curvature here. Where, okay. The new boundary K is surface measure. Surface measure on boundary K. And so and this is nothing else but n minus 1 dimensional Hausdorff measure. Measure restricted boundary K. And kappa boundary K of X. This is the Gauss omega curvature. To be precise, it's the generalized Gauss omega curvature. I will talk about it, why generalized and how this is exactly done. And okay, so we want to understand this, and so we shall explain the details. Well, they already something Elizabeth explained that why yeah, so how did one arrive at affine surface area? Well, she explained it. I mean, this was simply the analogy between the Minkowski definition of the surface, and yeah, and so let's denote by this the n minus 1 dimensional volume here of the boundary K. This is what Minkowski uses, just a limit. And it's 0, we have the volume. Now this is the nth dimensional volume of K plus T e to n. E to n is the Leiden ball with radius 1. And then we subtract here K inside. So this is also what we call the Minkowski definition here. And of course, this is just the same as if I take here the n minus 1 dimensional Hausdorff measure of this. And then, instead of taking here, taking a K plus T e to n, we just take K, and then for the other object, we take just the floating point. Then this is what Elizabeth already explained here. So we need to define the floating body. So let me make sure. A floating body K, and then with the straight brackets here, KT, is a convex body K such that each oh wait, sorry. So floating is a convex body. Sorry for that. Convex body contained in K such that each supporting hyperplane cuts off. So you say call it H. Cuts off. Set of volume T exactly. Okay. So this is clear. So we have K. Then inside here we have what is KT. And then whenever you have here supporting hyperplane of T, then it's said here this is volume T. And then to link this up with what Elizabeth said, then as a result of Dupin, it says the following. So whenever you have the situation here, so this is H here, T, K, then this hyperplane here touches KT at exactly one point. This point is the centroid of this intersection. So this is the intersection here I'm talking about. And so this point here where this hyperplane touches, this is the centroid. So this is what it said. So all these points form the floating point. And then unfortunately, and this was so the floating body there are convex bodies no floating bodies. In this precise sense. So this is, of course, for this what is going to follow. This is rather bad. But let me. So now. So Blaschke showed that if the boundary K is of class C to 2 plus, so it's twice differentiable or can be parameterized by a function that's twice differentiable and the curvature is strictly total. So if the boundary of K is plus, then and for sufficiently more floating bodies exist. Okay, and this and moreover, also what you showed was then that the limit t tending to 0, and then we have here the volume of K, volume KT divided by T to the 2 over H plus 1. So this equals Cn, and then Cn is all bounded K, kappa K x, 1 over N plus 1, d mu. This is also what you show. And also, I said that there are convex bodies that have no floating bodies, and the simplex is a case. This is such a case. There are no floating bodies whatsoever. And why is this? Well, if you look at it, so the geometric clue here is that here you have look at these angles here. And so you have this phenomenon that actually these extension of these lines they show basically here to the outside of this face. And so whenever you have such a phenomenon, so if you here usually it looks like this, so then here these tangents they meet here, but here they don't. And so this is the phenomenon. How this looks like in higher dimensions is another story. It has the same features, but okay, but geometrically this is where things go wrong. Okay, so now this is what showed, and so we don't have any problems here with this and this because this exists, and also Blaschke always assumed that his bodies were analytic. I mean, the boundaries were analytic. I mean, he didn't care about sheet classes. So I mean, so so this is also well defined, and this was continuous, and had was found. Okay, so then this is also, yeah, Elizabeth also explained that. Yeah.
Sorry, so the hexagon or something would be okay. I mean,
So
from what you explained,
yes,
if you had a hexagon or something, that would be fine.
yes, that's fine. This is fine. As soon as they move outside, that's bad. Yes, and then okay, I can explain well also quickly why, because you have here, say you are looking here at this line, right? Chopping off T, and then you move it here, and then suddenly you get what this shape here, these points that are the center of gravity. I mean, they form this swallowtail. All right, so yeah, so this is fine. This is well fine, and then also what Elizabeth explained is that okay, so this is here. affine surface area here, then we will explain that AS of T, okay? Because the absolute value determinant is the power n minus 1 over x plus 1, and then just for this volume affine surface area. And this is also, this uses here, this is explained it nicely here. This one. Okay, so then we have here a problem, namely that I mean, this is not defined here for all arbitrary complex bodies. So now I want to talk about it, how to circumvent this problem. So this was around 1990. There were basically, well, there was first of all the light price. And look, and myself, and they settled the extensions to general convex bodies. Yes, it was. No. So this and actually by three different approaches leading eventually to the same definition. Okay, so then what the approach that Elizabeth and self chose, so what we did, we modified the definition of the floating body, coming up with what mentions the convex floating body. So this is just also once again remind you, this was so KT, the convex floating body. So we have here the convex. So KT, this is just the intersection over all half spaces H minus, H plus, and then such that the volume of K intersected with H minus equals T. Right? So again, this is, so we have all kinds of hyperplanes here intersecting. Body chopping of T, and then inside you can also view it as an envelope here, but it's the intersection of all these half spaces. So if this is a hyperplane H, this is H minus. And yes, so we so this is the convex floating body, and note that whenever now you have here a supporting hyperplane, this could chop off here the volume strictly bigger than T. And it happens, well, in particular for the symptoms. All right, so that's something. Okay. And okay, so we modified this in this way, and And then we showed this modified formula right down so that then it's T times 0 volume of K minus volume of KT now divided by T to the 2 over n plus 1. Just Cn, Cn, integral boundary of K, kappa, K, or X. We have here 1 over n plus 1. The mu boundary of K. So just the same formula, except that now we have different objects, slightly different objects. All right. So and here, kappa K is generalized Gauss-Kronecker, Gauss. Okay, so what is it? Well, the problem here is the following. We know that, so let me talk here about the function f, say from U, which is a open subset in Rn, mapping to R, and say this is convex. So we can use this as a parameterization here of our boundary. And this here is almost everywhere differentiable. But there are convex functions that are not differentiable on a dense set. Okay, so if you want to come up with, so suppose we have such a function, you want to come up with a second derivative, then on a dense set, this function, the first derivative is not defined, so the second derivative does not exist anywhere. So this is very bad for us. Well, let me let me give you a simple example here. So you take here the function x squared, and then you take here sequence converging to 0 here. So you can take, for example, here 1 over k. And you take these points here, and then you take the convex hull of all these points. So you have this here, and then here, well, cannot draw it. So then this function, this new function here, has, of course, derivatives here in all points different from 1 over k, but there's no derivative in the point 1 over k. So the second derivative here does not exist. So this is a typical example. You have now here just where one point the derivative doesn't exist. Well, so then you sum up over these examples, and then you get 4. Well, on the other hand, I guess that when you see this, you cheat it, because it's obviously here this function should have a second derivative, right? I mean this is that you have here these corners here, okay, but the closer you come to 0, the smaller these corners are. So I mean, well, legally this function, this new function here is not differentiable. It's not twice differentiable at 0. But morally, it certainly is. So, and this is about this other degree. I erase it. Okay, so yes, so okay, so let's so f as usual, this is this function here convex, and say it's defined on an open subset of Rn, and so on. So this is twice differentiable in the generalized sense at x0 if there are, first of all, a neighborhood so we call it B of x0, and a linear map. And this linear map we call just D2 after x0, so linear map from Rn to Rn, such that for all x in B of x0 and all subdifferentials df of x. So subdifferential is the following. So if you have f of x minus f of x0, this is bigger than the f of x0 x minus x. This is subdifferential at x0. So here, the more subdifferential dfx, we have the following: the norm of df of x minus df of x0 minus d2f. This here applied to x minus 0. So this is the Euclidean norm here. This is less than theta of norm x minus x to 0 times norm x minus x0. You have it, and then of course you like usually the limit of t tending towards 0 of theta of t is 0. Right? So we have this type of condition. So now you see that this is good because here this is not the first. Well, if the first derivative exists, then this is it. But in general, this is just a subdifferential. So at the point x, there may be many, like we saw in this example. But so for all those, you have to have this. Now, one thing you observe is the following: that the closer x gets to x0, the closer dfx approaches dfx0. And it in particular turns out that at the point x0, this function is differentiable. It's not only that there's a subdifferential, but it's differentiable, and df of x0 is actually. Okay, so this is this definition, and then there's a marvelous theorem of example. Which says that f a convex function f is almost everywhere twice differentiable in the generalized sense. And this result is 1938. Okay, so now I think, yeah, now we want to go through the argument here how to. It's gone? No. We want to go through the argument how to prove it. Okay, so proof of star, and star I mean this. So the rough idea, the general idea, how to do that. So we have K here. And then inside here we have KT. And so these things show up here. So what do we really have here? Well, we want to compute here this difference volume and divide by t to the 2 over n plus 1, and then take the limit. Well, how do we do this? Well, you can take here such an infinitesimal surface area. And then you consider here this, I don't know, call it a cylinder or so. Cylinder here, and we do it here. So we get a Riemann sum. So what we get here is the integral of the boundary of K. And if this here, this is the height, x, right? So then we integrate here the height x, and then the nu of K of x. So, with a lot of luck, I mean, then this should work out. That this is our volume. It's a rough idea. I mean, how we. So first step. I mean, this should kind of work. And then, what about this height? So and then this is nice because here at this point, so we have, it looks like this here, right? It looks like this. And here is our point x, and we know that that here we twice differentiable, and therefore it's in the generalized sense, and therefore we can approximate here the boundary of K by an ellipsoid or an elliptic paraboloid. And what else? So we're looking here at this point, kind of the nearest point or something like this. And then we take here a supporting hyperplane to this point here. And so then we want to compute here this height, but this is now clear. This is because this is now an ellipsoid or elliptic paraboloid, and it's a cap of that. So, what we get here for this is for this height, this is something like kappa k of x raised to the power 1 over n plus 1, and then times t to the 2 over n. Oh, this is wonderful, because then, we can plug this in here. By this number, this disappears, and we have this form. Yes, so but this is a rough idea. Now we need to make it more precise. This is done in the following way. So first of all, well, we may suppose that 0 is an interior point K, or it's the centroid, whatever. I mean, it's important thing. It's an interior point. Then we have K, and then here we have KT. Somewhere here we have 0, and now we have here some infinitesimal surface element, and then we want to compute here this volume. And well, it's not really difficult, because we have here. So what's this volume here? It's the volume of the whole cone here minus the volume of the smaller. And so what is the volume here of the whole cone? Well, this is just the surface this infinitesimal surface element times x, and x is the normal here. So so this is the height here, the height, and then we multiply by 1 over n, and then we have here this times here this whatever the surface element. So altogether, what we get is that the volume K minus the volume T is actually equals 1 over n, the integral of the boundary of K. Then we have here x. This is the normal to boundary of K, x. And then we get here, so this will be this whole volume. We have to subtract this. So we get here 1 minus, and then we get here x t, the normal of xt. What is xt? Xt is this element here. So this is xt, and if this is x, and they are on this line here, so this is xt is on the boundary of kt on the line between 0 and x. And then we divide here by everything here is raised to the power n, and then we get the d mu boundary of k. So we have this formula here. And now we, of course, we just divide here by t to the 2 over n plus 1, right? And then what we observe is that this thing here converges, in fact, towards kappa x and then raised to the power 1 over n. So it seems we're done here because, well, we did one thing, we used the Beck's theorem. So we need actually a dominating function, an integral dominating function here. And this is not so obvious what that is, or which one that is. And we need to work there a little bit more. Yes, any question? Okay. So we want to apply the Beck's theorem. And we need a dominating function for that. So, okay, so now we come to the rolling function. So Blaschke said that a Euclidean ball of radius or with radius r rolls freely in K if it can at each boundary point x and boundary k such that it touches boundary x and it is contained in K. Okay, so this is obvious. So we have any x here, and then we can place our ball here like this. It's contained, it touches the boundary there. Now, for example, if you have a square, you're in bad luck because there is no ball of positive radius that rolls freely there. And yeah, so Blaschke used this here, and actually what he showed was that whenever you have a boundary of class C2 plus, you find a ball in there that rolls freely, a ball with positive radius that rolls freely. And this was what he showed. Okay, now. So, our Elizabeth and I, we came up with a quantitative version here. Version. Ball rolls freely. K here is the following. So we introduce here R of x primo for all non-x minus z. And x is on the, is in the boundary. Such that b to n of x minus z, and then here we have the norm of x minus z, that this is contained in space. So here in the for the square, then we could place here a ball, right? And then this radius here would show up here, but it's also clear that we take the supremum. So whenever we have a point here, this would be the ball of largest radius contained in there. And this is what our x is. Yeah. What? Oh, the brackets. Yes. So, and then what we showed there here was that so if K is a convex body, then any alpha 0, 1 over r to the alpha, mapping from boundary of K to R, well, actually, not just to R, to 0 infinity, is the back integral. Well, we showed a distribution of inequality first, and then we could easily follow from this that this function here is in the back integral. Okay, so we have here, so alpha is between 0 and 1. 1 is not allowed. Any number smaller than 1 is allowed, and this is still integral. So now we're done with our proof, almost. Leave this here. Almost done. So, okay, so what we have is that kappa x, this is less than 1 over r of x. Yes, because this is r of x is sitting inside, sorry, the ball with radius r of x is sitting inside. So we have this here. What? Oh, yeah. So to the power n minus 1, we have, because we have n minus 1 directions. So we have this. So from this it follows that kappa of x to the power 1 over n plus 1, this is less than 1 over r of x raised to the power n minus 1 over n plus 1. So we want to show, we need to show actually, for this we have this dominating function here, which now the dominating function here will be this. And we know that as long as alpha is not is strictly less than 1, this is integral. So to look at it, if n gets bigger, we get closer to 1. So we barely made it, but we made it. And so this will be here our dominating function. I mean, of course, there are some details. I mean, but this takes a lot of time. Well, there is okay. I still have a little bit of time. And I want to mention at least one result of random polytopes. Yeah, so what Matthias described here, what was done is, so you compute here the expectation of well, call it k, and then mu k. So this is the back measure of k. Then this is just the integral k n times, and then you have this volume of the convex hull of n chosen points, and then v mu k of x convex. V mu k of x. Okay. So this is the expected volume here of such a random polytope, and then what one gets here is the limit and in the infinity of k minus mu k divided by volume k divided by capital N to the power 2 over n plus 1. This actually, this limit exists, and this is C and tilde affine surface area of K. This is a different example. And here we are here in the nice position that actually this holds for all K. This holds for all K here. Very often, okay, before I say that, I mean, so the first to settle this quantity was Rani, and he did it, I think, for C3 plus or something, and then I did it for arbitrary complex bodies, and the important ingredient here was exactly this, because also there you need to apply Lebesgue's theorem, and you need to interchange limit and integration. So this is all right. So yeah, but what is striking is that this is almost the only result here where we got rid of this condition C2 plus. And most other, and what is so pleasant about C2 plus? Well, the curvature is a bounded function, so you don't need any dominating function. Okay, so I don't want to make enemies. Thanks.
Has any question?
Maybe I can ask a question about a small remark that you made earlier about the convex floating body and how
Yes.
certain supporting functions can cut off a volume larger than T.
Yes.
Do those caps have to contain a vertical corner? I mean,
Sorry?
if you take such a cap which has volume greater than T,
Yes.
then does that have to contain a corner to go to the boundary?
Yes, probably.
Is there a way to detect corners just sitting on the floating body? By looking
Oh, does it have a corner of the floating body?
No. So if I take one of these supporting.
Well, I can show you an example.
Oh, okay.
Yes, that is probably easy. So if we have here a triangle, simplex, and here we have, it looks like this here. This, these points look like this. So then you have here this hyperplane. I think maybe it crosses there. So this cuts off exactly T, and also this. But then you also have this hyperplane here. And so sorry, then you also have this hyperplane here, and this cuts off more.
Right, but if you look at that hyperplane and you look at the cap above it,
Yes,
that somehow captures the two corners
yes,
over
it
there.
captures.
So will that always happen? Will those caps always, the portion of the boundary that they cut off, will that have to contain?
It looks like
If that,
it looks, yes, yes.
This cannot happen for a smooth body.
I mean, what I meant
No.
is this capturing this somehow locally? Like if there's a smooth part, then there the caps cannot be larger than T.
But if you can, what Elizabeth also said, so if you can make it smooth here, right? And then all you have the same phenomenon here.
Ah.
If you, okay, so here I made it rather big, but do the smoothing here just a little bit, so.
Okay, okay.
So then you are in the same position.
Same problem.
So any other?
What, the density being uniform, is that
Yes.
crucial there, or is that possible to get some?
Yeah, yes. This is, Elizabeth and I, we have actually another paper. It's about choosing the points on the boundary. And then we have for arbitrary continuous density. This actually, I thought about this also showing this.
You have similar for variance, like Matthias in this talk said you can get in this even the variance with the same, except the CN being different.
No, we actually, we never considered that.
So for that result, that integrability result, that holds for example, C2 plus domain, where you can place these balls. Is it?
Yes, but if K is C2 plus,
Yeah, then
this is a bounded function.
right. So this is one particular way of getting a dominating function.
This,
Yeah. So then you will use it there to dominate that.
yes.
So is there any other ways known?
No, it's the dominating function here is related to the curvature.
Right.
So in this case, whenever you so we are here at the boundary, and then we have here our ball, then we know that we have a relation here between the radius and the curvature. So this we need.
And is there any intuition behind this result? Like, why do you think this is integrable for any power alpha between 0 and 1? Like, why did you guess this?
The square. Or this the cube. And then you do this computation, and then very quickly you realize what's going on, and then you once you saw that, you go past to a polytope. And the phenomenon there is very similar, and then you pass on to an arbitrary convex body because this radius here, the rolling function is upper semi-continuous. So you can pass through a limit.
Does something nice happen if you replace, say, the uniform measure with a compactly supported log concave measure, or is there like a measure version of
Well, I mean, this can be done. Let me put it like this: it can be done, I guess. But we never looked.
Are there any other questions? Not, let's thank the speaker again.